We looked at programming relativity and gravity in a Planck universe based on the mathematical electron model. We now need a scaffolding for our nascent universe. Here I assign a base object, which we could call a Planck pixel, for it incorporates the indivisible Planck units, and so resembles the notion of a Planck black hole. The simulation is then quite simple. We just add these Planck pixels one by one. For time th equals 1, the Big Bang start, or start of the simulation, to th equals simulation end. Although we're just adding Planck units, without particles, a 14.6 billion year old Planck universe resembles the cosmic microwave background of our universe to within 5%, which is about the proportion of particle matter. Yet the only variable that we are using is the simulation clock itself, this th. In this table, 10 to the 61 Planck pixels have been added since simulation start. This is equivalent to 14.6 billion years. Here are the calculated values and the observed values of the cosmic microwave background. And so by choosing th, we can choose whatever th we want, we can calculate the mass of the universe and the volume of the universe, and so the mass volume density of the universe at that th. Th for us is 10 to the 61. And then we can simplify the radius of the universe is simply this expansion in these Planck steps. Now, here in temperature, we find something else. Now, the key point to note here is that although mass and length are increasing in incremental steps, th equals 1, 2, 3, 4, 5, and so on, the radiation properties are increasing in a square root progression. And so are marked by the square root of th. And so here we can calculate the temperature of our Planck universe for any th using this square root. Now, we find that the mass volume formula used th squared. Temperature formula uses square root of th. So what we can do is combine both these formulas to eliminate th itself, and then we end up with a constant of proportionality, and this constant resembles the radiation density constant, which we find here. And then next we look at the Casimir formula, and here instead of area we're taking our Planck units, the size of the universe itself, and so if the distance is 2 pi times the square root of th, which is our radiation variable, then we find that the Casimir force equation, this one here, actually is the radiation energy density. So actually, in this model, in this context, the Casimir formula is simply measuring the radiation density of the universe itself, of our Planck universe. Hubble constant, black body frequency, which we'll come to later on, is also a square root. Now the cosmological constant is approximately 10 to the 121 units of Planck time. Now we want to know when our simulation will end. Now our simulation began at th equals 1, and the temperature was Planck temperature divided by 8 pi. So the simulation will presumably end when we're at absolute zero, or 1 Planck unit above absolute zero, because then the simulation can go no further. Now we don't know what this temperature might be, but for simplification we just take the inverse of Planck temperature, and we find that if we do that, the universe will end after approximately 123, 10 to the 123 units of Planck time, which correlates to the cosmological constant. So the inverse of Planck temperature may be a good guide as to when a simulation will end. Now, I talked about Planck pixel, so we could say this 1 is our Planck micro black hole. So TH universe is 1, and 2, 3. So the circumference increases 1 by 1 by 1, pixel by pixel by pixel. But the radius is the square root. So if we made this, it's called a Theodorus spiral, just by adding our pixels together in a spiral pattern, we get our linear mass volume and our spiral radius, the square root proportionalities. Now also, if we expand the universe in a spiral pattern instead of just in a spherical pattern, then we could increase our universe, grow our universe to the left or to the right. So we could have a left spiral or a right spiral. And so any left particle in a left-handed universe, although identical to a right particle, would actually have a slightly lower energy. And so we could find through this method that left particles, left states, would be slightly different to right states. And this could reflect on the matter-antimatter paradox, there's the chirality, and so on and so forth. One further final point is our mathematical and physical constants could also be a function of TH themselves. And so their position would depend on TH. For example, we can calculate pi using integers. And these integers would just be the expansion of the universe. And so as the universe gets larger, numbers like pi, and so presumably the physical constants, also become more and more precise.